Starting recording. Let me launch the class there. Pre-calculus. Good morning. Good morning and welcome. I see there's a question already up. All right, cool. And let's start with a practice quiz, though. Actually, can y'all hear me? Somebody give me some feedback. Great. All right. Let's start with the practice quiz. And
Start recording.
Number 1. This is going way back.
Bianca had a question.
First reaction might be, oh, I've totally forgotten how to do this. But try to see if you can reconstruct it. Find the equation of the line that passes through these 2 points.
Can you hear us?
1, 3,
Hello?
and 5, 11.
Can you hear us? Hello? No one can hear us.
So this is back from college algebra and intermediate algebra.
Okay, well the professor can't hear us.
My volume was turned way down. Did somebody say something?
Yeah, we're asking if you recorded yet.
Oh, yes, I did. I just started. Thank you very much for checking. It is going. Thank you, Kylie. Will you all enter the word spot if you have the spot check for 9.5? You have that 75% completed. Alright, so I've got a question here. How many of you realized that one of the first steps is to find the slope? And you take the difference in the y, it's the real formula, y2 minus y1 over x2 minus x1, the difference in the y's over the difference in the x's, coming up with 2. So don't type anything if you didn't realize that, but if you realized and you had done the slope, it's one of the first steps, type a yes. And let me just see How many are remembering to type, get the slope? Alright. Now, were there many of you who were kind of stuck after this? Not quite sure what to do after getting the slope. That's what I would anticipate. Perhaps if I hadn't done this in a really long time, I would think, I might get that, but then there's two different ways to go about it, and I want to review this stuff. The easier one to remember, you might remember the equation of the line, y equals mx plus b. If you remembered that, you can work from that and come up with the equation. The easier one is if you remembered y minus y1 equals mx minus x1. This one makes it really easy to plug it right into, but you might not have remembered this one. So let's suppose I had remembered this. Now let me show how easy it is to do it with this. And then we'll go over to here, in case you hadn't remembered this, how you could still have constructed it and got the same answer from here. So we just take, we'll call this point x1 and this one y1. Not only because it's the first point, but it's smaller numbers than that. So it'll work a little bit nicer. We'll get the same answer though if we'd used 5 and 11. I'll do y minus 3, plug in this m2, x minus 1, and then y minus 3 is 2x minus 2, y equals 2x plus 1. Now, this is not just the equation of a line, but it's a rule for how you take any input and get its output. It says if you double the input and add 1, you'll get the output. Double 1 plus 1, you get that. Double the 5 to 10 and then add 1, you'll get that. It's a rule for getting from inputs to outputs each time. Yeah. And then, now, suppose you hadn't remembered this though. And by the way, these have names. This is called the y equals mx plus b, that's slope y-intercepts, called the slope-intercept form. This one is called the point-slope form. Because you're given a point, x1, y1, and a slope. It's just, the names come from the material that's given there. Right. Suppose I couldn't remember that though, and couldn't remember the easy way to do it. I could still have constructed it like this. The only thing I know for sure is the 2. So I'd put the 2 in here. I don't know what the b is, because neither of these has an x-coordinate of 0. If one of these points had an x-coordinate of 0, I could just substitute it right in and I'd have my b. But there's a way to get to the b. These are called constants because they never change. These two are variables. They get to play the what-if game. If the x is 1, the y is 3. If the x is 5, the y is 11. So we can do the what-if game with either one of these points. If we substituted 1 for the x and 3 for the y, or you could substitute 5 and 11, doesn't matter. But you just substitute 1 for instance of it. And then, minus 2 from both sides. You'll get b equal 1, and then this is the total equation. You substitute 1 for the b. Either way, we're getting the same answer over here. Alright. Type in a little bit of feedback, and this time I'm going to ask you to type in a little bit more. instead of just saying, got it or not, type in, I forgot this, but could do this. Give me just a little idea of where you were at. Everybody's going to type in a little bit. I forgot this, but I got this. I got the slope, got stuck, I got this, so on. Everybody just give me a little feedback if you got. I would probably gotten the slope and gotten stuck if I hadn't done it in a long time. I got the slopes open. I remember both. Alright, great. Okay. Alright, so this is kind of reviewing some fundamentals that as you move on in math, we can't forget any of this stuff. We have to, you'll be recycling this a bunch when you go into calculus. Equations of lines and all that stuff will be hugely important. And it kind of brings up the point too of we've only got 2 weeks left of regular classes, and then we have the final exam. And I'm going to take you to the Canvas homepage here for this course. And if we look in the modules, I'm going to take you down. Now, I'm going to make another module for exam 4, and I'm going to make a practice exam for exam 4, because that's in a week that you have exam 4. But the final exam, let me take you to here, the final exam. It'll be uploaded on Thursday, May 14th, the normal time, 10:30 a.m. Will be available for 2.5 hours. You must complete it, get it back to me by 1 p.m. Alright, the final exam is normally worth 20% of your total grade. This semester, if the final exam hurts your grade, it'll only count as 10% of your total grade. If it helps your grade, it'll be worth 20%. And then it says, please see the final exam review problems and bonuses available for completing them. So, I'm going to hit the back button. Right above this, it said final exam review problems. Click on this, and they're in 2 different formats, and it says completing at least. Now if I click on one of these formats, you'll see it comes up here, downloads it, open it up, and it's just a listing of a bunch of problems from the textbook. And so completing at least 50% of those problems will earn you a homework grade of 100%, which will replace your lowest homework grade. Completing at least 90% of these problems will give you the same result, 100%, for your replacing your 2 lowest homework grades. So I'm not putting any penalty on not doing these, but I'm putting a rather large incentive. Getting kind of the overview of what you learned in this class will be really, really helpful as when you go on to the next classes. The exams do a lot more than just check to see if you really learned the material. They provide the structure so that you wind up being forced into kind of integrating the material together. And any questions on final exam and the review problems for the final? And how many problems will there be on the final exam? I don't think in terms of number of problems, because I can easily make a 1 hour, it depends on the course and the type of problem. I can make a 1 hour exam with 50 problems, and I can make a 3 hour exam with 10 problems. It's not going to have a tremendous amount of problems. It's just only slightly longer than the normal exam. But the big thing about the final is it's covering everything for the whole semester. So just a little bit longer than a normal exam, in kind of length of time it would take. All right, let's go to another practice quiz problem. And number 2. A is 5, B is 4, cap A is 47 degrees. Find C. Now, what I'm introducing to you here, it's in a practice quiz, but it's actually just introducing an idea. It's the standard way that triangles are set up. And the standard way is this. Now, this is a right triangle. Find C in the right triangle where cap C is 90 degrees. Alright, so the standard way of setting up a triangle is if you make a right angle and you label these sides. Now it doesn't have to be cap C, but more often than not, cap C is the 90 degree. And the other two are like A and B. Maybe this is A, B, C, or A, B, C, it doesn't matter. But opposite cap A, now these are the angles. So cap C is the 90 degree, and cap A, if it's a capital letter, it's an angle. Now, some textbooks, you see, because we like to have, like remember when we were doing cosine, sometimes we'd have cosine theta, and if it was a Greek letter, that was kind of an indication that that's likely an angle. So sometimes textbooks will have like alpha, beta, gamma, instead of A, B, C, like this. And our textbook tends to do that a fair amount with the Greek letters. But those are Greek letters corresponding to A, B, and C. Opposite A, angle cap A is little side A. Opposite cap B is little side cap B. And opposite cap C is little side C. But they won't draw this triangle for you. They'll just tell you this kind of information up here. And when they tell you this information, they assume you know the structure. That the angles and the opposite sides, the little letters are the length of sides, the big letters are the angles. Alright, so that's the setup. So now go ahead and find little c. Let me take out this to make it So suppose all you know is cap A is 5, or cap A is 47, and little a is 5. Then find cap C. And suppose you don't know little b. Okay, 30 seconds more. Alright, so we know that the A is 5, and we know cap A is 47. How do I get C? I'm going to need some kind of trig function of 47 degrees that uses the one that I know and the one that I'm trying to find. And from the point of view of 47 degrees, this is the adjacent side, this is the opposite. This one, from any point of view, is the hypotenuse. So we want opposite over hypotenuse. But that's the sign, so katoa, opposite over hypotenuse. So I want to take the sine of 47 degrees is 5 over C. And then I'm going to multiply both sides by C, or if it's one fraction equals one fraction, you can do this. These multiplied together will equal each other. So C times the sine of 47 degrees is 5 times 1, or C is equal to 5 over the sine of 47 degrees. C is equal to, and I'll punch this out in my calculator, check my mode. I was in radians, so I have to go back to degrees. And then I'm going to go 5 divided by the sine of 47. So we got our side length from this. Alright. And give me a little feedback on that. A 1 if you were able to get that ahead of me. 0 if you weren't. And any fraction if you were kind of on your way. Okay, so this kind of problem becomes one of the very common problems in a trigonometry class, which is called solving a triangle. And solving a triangle means finding all the 6 parts of a triangle. There's 3 angles and there's 3 sides. And we'll be getting into solving a triangle. I think it's going to be, let me look at our schedule. We'll get into that really on Wednesday of this week, into more details about that. 3. Solve a 2 sine x equals negative 1, where x is between 0 and 2 pi. Give you a minute for that. Alright, I'm going to stop, and I'm going to divide both sides by 2. Got to isolate the variable as much as possible. Now this is a function, a trig function of this. I can immediately do inverse sine of this and punch that into my calculator, but I will only get one solution if I do that. But if I do this first, it will remind me that there's more than one solution. I make this negative 1/2 either on the x-axis or on the y-axis. Since this is the sine function, I put it on the y-axis. If it was a cosine function, I'd be putting it on the x-axis. Okay. Now, I see that there are 2 such angles, over here and over here, that are going to be solutions to this. One of these when I punch this into my calculator, it would tell me, but it would tell me in the wrong format. And let's just do that. If I took the inverse sine of both sides, these kill each other off. And when I punch this into my calculator, and I make sure I'm in radian mode, so I have to change back, I just had changed it back into degree mode, and I do inverse sine of negative 0.5, I wind up getting x equals negative 0.5236. I round that last one off. Now, I could have written my answer down this way, but I think I could have figured out what that was without a calculator. I remember that the sine, inverse sine, is going to be in these 2 quadrants, and so quadrants 1 and 4, and quadrant 4 angles will be reported as a negative angle, and so I know that this was going to be recorded as a negative, and it was going to be negative, and that's really 30 degrees, or pi over 6. And then I suspect this is really pi divided by 6, so I'll double check that. I'll put pi divided by 6 into my calculator, and I'm getting exactly the same thing, so that was right. So maybe I would have preferred this answer. When I can give the exact, why not? Alright. Now, the problem with giving the answer like this is that's not between 0 and 2 pi. So the calculator will give it to me, but as in the wrong format, as a negative angle. So what is this as a positive angle? It's 2 pi minus pi over 6. It really is x equals 2 pi is 12 pi over 6 minus 1 is 11 pi over 6. Okay. Then my other, that's just one of them. My other answer was these two angles will both have a y-coordinate of negative 1/2. So the sine of them will be negative 1/2. Now this one is such that its reference angle is pi over 6. But the whole angle was pi plus pi over 6. So pi is same as 6 pi over 6 plus 1 pi over 6, 7 pi over 6. I'm getting these two angles. Now, I didn't have to give them that way. I could have stuck with this one. That would have been okay, the negative 0.523, except that that negative 0.523 is not in between 0 and 2 pi. So I would have added 2 pi to that. So if I'd have done that, I'd have gotten 5.7596, something like this. So this would have been an acceptable answer too. And then 7 pi over 6 is the same as 3.6652. And that would have been fine too. I could have given the answers in this or like this. Alright. Now, I'm going to ask for more detailed feedback on this. Not just a 1 or a 0, but like I got part way and I'm lost, I got it, I got the whole thing, or I'm okay with getting one solution, I don't understand getting two solutions. Just give me a little sentence. Everybody just type in something, where you're at with this kind of problem. Alright, let's go to the next one. Number 4. We're going to shift things again. We're going to take this right triangle. We're going to call the sides A, B, C. And opposite of cap B is going to be little b. Opposite of cap A is little a. We don't know what that is. Opposite of cap C is little c. We don't know what that is. And we know that cap A is 37 degrees. Find little a. Give you a minute. done that. "30 seconds more." Alright, so the implication here, I should have put this in here, is that that's a right angle. You don't know how to do it if it's not a right angle. But on Wednesday, that's going to be a topic. Is we're going to learn on Wednesday how to solve triangles when there is no right angle in them, non-right triangles. But today, before we do that, we're just kind of reviewing some basics of how you'd solve a right angle triangle. So find little a. Well, the only non-right angle, well, really when I know one non-right angle, I know the other one, because that one's got to be 90 degrees minus 37 degrees. But if I take the one angle that I'm given here, that I can do a trig function on, I generally don't do trig functions on the 90 degree angle. I want a trig function of 37 degrees that uses the one side that I know and involves the thing I'm trying to find. So, what trig function would I use of 37? Well, from 37's point of view, that's the hypotenuse from any point of view. But this is the adjacent, this is the opposite. I want opposite over adjacent, that's the tangent. So KTOA, opposite over adjacent. So I want tangent of 37 degrees is equal to A over 4, opposite over adjacent. And then I make this over 1, I do the cross multiply. A times 1 is A, tangent 37 degrees. And then I punch this into my calculator. Tangent, well, let me check my mode. I gotta go back to degrees again. Tangent of 37 times 4. And I'm getting 3.014. And that would be it. And always opposite the smallest angle will be the smallest side. Opposite the biggest angle will be the biggest side. Opposite the medium-sized angle would be a medium-sized length of the side. It will always be the case in any triangle. Alright, this one, I want to know whether you got it correct or not. So 1 if you got it correct, 0 if you got it incorrect, and you can tell me anything in between. Let's go to number 5. you to solve this equation. Cosine squared x is equal to 1/4, where x is between 0 and 360 degrees. I'll give you a little time for that. Alright, so I'm going to square root both sides. You could also subtract 1/4 and factor, but just do this. When you square root, you have to insert plus or minus. So I get cosine x is equal to plus or minus. Square root of 1 is 1, square root of 4 is 2. So I get plus or minus 1/2. This is two different problems. Cosine x is 1/2 and cosine x is negative 1/2. If I go cosine x equals 1/2, I put my 1/2 on either the x or the y-axis. Since it's cosine, I'm putting it on the x-axis. I'm either going to be up here or down here. And this angle is a 60-degree angle. And this angle down here would be negative 60, but I have to be between 0 and 360, so I'm going to take it to be 300 degrees. So I'm going to get two answers. X equals 60 degrees and 300 degrees. On this one, I put my negative 1/2 on the x-axis again, up here or down here. Those are the two angles that have an x-coordinate of negative 1/2. And this angle is 90 degrees plus 30 more, 120 degrees. And then this one down here is 180 plus 60 more, or 270 degrees back up 30 degrees, 240 degrees. And actually, before I gave these answers and circled them, I'd probably put them in order from smallest to largest, so it's easier for somebody to see what's going on size-wise here. So those are my 4 answers. All right, now give me a number about how many answers you got. You might have gotten 0, you might have got 1, 2, 3, or 4. Give me feedback on the number of correct answers you got. Okay, and like if you made a tiny error, yeah, you can put something what you did. Okay. Alright, so what I'm noticing is nobody's putting 4 answers. It's, except Josiah. Yeah. Okay. So it's a little yes. Okay, forgot the plus or minus sign. Okay. Okay. All right. Plus and minus. Now, that's like if you had x squared equals 9, we tend to want to jump and say, oh, x is 3, but only if we get in that habit of always putting a plus or minus when we take the square root of both sides, will we remember to get that plus and minus 3. And so what's happening in a general trig function? Well, general trig functions, if you didn't have this squared to start the problem, if it was just cosine, you would usually get double the number of solutions. Instead of, if you're in one rotation, instead of 1 solution, you get 2. And when you have quadratics, where you have x squared instead of x, that also tends to double the number of solutions. So that's why we got 4 solutions. We got them doubled in 2 different ways. One with this and another with this. And that's the tendency in second degree polynomials tend to have 2 solutions. Third degree tend to have 3 solutions, and so on. It's actually the maximum number of solutions that they can have. All right. So that takes us through our practice quiz. And Kylie, I think you had written down that you had a question on a certain problem. What problem was that? Number 5.
I got up to the quadratic form and got the answer, but I don't know how to apply it to the original equation.
Okay, so it was 45. What section is that?
9.5.
9.545. Let's look at that. And the interval is from 0 to 2 pi. And solve this equation. And if it factors, we factor. Did you get it to factor, Kylie?
No, I couldn't figure it out, so I just
Very good. If it doesn't factor quickly, just give up and go to the other one. I'll try it real quick and see if I can get it to factor. And it's got, the 3 has got to be broken up, 3 and 1. Then I do the signs next. They have to multiply be a negative, so one's positive and one's negative. I'm not sure if it's plus minus or minus plus, but if I have them backwards, you just switch it. If I get the wrong sign, you just switch these and it'll change the sign. And then 2 There's only one way to do it, 2 and 1. But if I put the 2 here, I'm getting something way too big. If I put the 2 here, I'm not going to get a 2 middle term, I'll get a 1 middle term. So this, it doesn't factor. So the only way to do this is with the quadratic formula. So I'm going to do, if you recall from last time, you can use this, u equals, so you're creating a new letter. And then I'm going to rewrite the equation. And now it is exactly a quadratic equation in the letter u. So then the quadratic formula is u is equal to, now it's negative b plus or minus square root of b squared minus 4ac all over 2a. And the a is 3, b is negative 2, c is negative 2. So stick them all in. The negative of negative 2 is positive 2, plus or minus. When you square something, you always get something positive. 4 minus 4ac all over 2a. And then two minuses make a plus. This is 6 times 4 is 24. 24 and 4 is 28. 2 plus or minus square root of 28 over 6. I might continue to, like, I could pull out the square root of 28, make that square root of 4 times square root of 7 and reduce it. But in the end, I'm going to have to punch it into my calculator anyway. So I'm just going to state that there are two answers. U is equal to 2 plus square root of 28 over 6. And u is equal to 2 minus square root of 28 over 6. Now I punched each of these out in my calculator. Plus square root of 28, I hit enter, and I divide that by 6, I'm getting 1.21525, something like this. Alright, now, let's come back. I couldn't circle this and say I'm done with my problem, because the original problem didn't have any u's in it. I have to go back and figure out what x is. So replace u with cosine x. Now, it says the cosine is something bigger than 1. Well, a cosine of any angle at most can be 1. And if I type in inverse cosine of that, I'll get error on my calculator. And this has no solution. Then we go to the other one. So u is equal to, I'm going to type 2 minus square root of 28 divided by 6. Negative 0.54858, and then this one is just like we were doing in the practice quiz. If I just type in the inverse, oh, now this is the cosine, go back to cosine. If I just type in the inverse cosine of this, the calculator is going to give me one answer because it's programmed to make it into a function. but there are two possible answers. I put this negative 0.54858 on the x-axis. I'm going to get this angle and this angle. So x is equal to, and I get this one, the first one, by typing in the inverse cosine. So I'm going to take the inverse cosine of that, and I get, now, I was in the wrong mode. I came out with 123, but I'm going to check my mode. It was degrees, so I'm going to change to radians. And then I'm going to say, do it again. And this time it tells me 2.1515, if I round that. Okay, so that's this angle right here. That's one angle. That's one of my answers. But this angle down here is also 1. And it's the same angle, but in the opposite direction. So if you had it in the opposite direction, it would be negative 2.1515. But that's not between 0 and 2 pi. So then I would add 1 revolution. And then when I put that together, I'm going to get 4.1317. These are my two answers. Right here. Does that answer your question, Kylie?
Sort of. The book has a different answer than actual decimals.
What does it have?
It had cosine, arc cosine times 1/3 times 1 minus the square root of 7. 2 pi minus arc cosine of 1/3 times 1 minus the square root of 7.
Okay, so what they're doing, and either format is fine. Whether you give it this way, the way I did it, or the way the textbook. I'm not crazy about the way the textbook's giving it as an exact answer, but let me show you what they were doing. When we got this right here, just get some room. And I see why you have a question about that. Right. So let's take this right here and replace this with cosine. U is become cosine x. And we have 2 minus, now square root of 28. That's the same as 4 times 7. And that's square root of 4 square root of 7 over 6. Now, square root of 4 is 2. So this is the same as cosine x equals, now I'm going to break it up into two separate fractions. 2 over 6, and you can only do this if the denominator is one number, that you can break each term up over that number. And then this cosine x is 1/3 minus the square root of 7. And then if I take the inverse cosine of both sides, would get x is equal to the inverse cosine of 1/3 minus square root of 7. That's kind of what the textbook was giving, but that's only this answer. And then the other answer is the negative of that plus 2 pi, and so on. And it's kind of, I think it's more complex the way they're doing it. I'd prefer to do it like this.
So would you prefer us to do it in decimal form?
Yes, the decimal form. That would be my preference. And it's simpler, it's quicker, and it's easier to understand. So, great question. All right, other questions? You know, a lot of people don't have microphones, so you can type in a question if you've got one. And if there's no questions, then, all right, now this class goes until 10:15, so let's take a 14-minute break, and we'll start again at 11:45. Alright, we will start up again. 10.8 vectors. So you notice that we are making a big jump to a much later section. We were in 9.5 vector equations, and then we're jumping all the way over to 10.8 vectors. And the reason for this is a very important topic for this class, and it should come kind of like as our last day of class. But if that happens, then we don't get really any chance to get a practice quiz on it to make sure that you kind of got the basic ideas on it to reinforce it. So I juggled the schedule to move it up a little bit since it's quite important. Alright, so we're going to start with a basic question. What's a vector? And the answer would have to totally do with your exposure if you kind of had an instinctive response to it. And some of you, if you've had a little bit of science classes and maybe a tiny bit of physics, have already been exposed to vectors. But the answer is that it's something that conveys both, or shows the essence of it, both magnitude and direction. Numbers contain the magnitude. 5. It's pretty clear that's a magnitude. But there's no direction with it. And so how do we contain both? We're going to have to do something like this. We will take this and we will put, this will be our vector. It looks like an arrow, but the thing that's important about it is how long the vector is and the angle at which it's cocked. Now, we can move this vector all around and we call it the same vector. This vector is the same as this vector. It's the same as this vector. As long as it's the same length and going in the same direction. Now, if I was better at keeping it in the same direction, you'd be able to see that. Now, why would you be able to move this all around? Why? We use it often for forces like the wind. And the wind is kind of, blowing in this direction, and it has this kind of, magnitude. And we put a longer arrow for a bigger wind and a shorter arrow, but if it's always going in that direction, we can move it wherever we want to. So it's very typical that we use vectors to show forces, although they can be very versatile and use other things besides forces. And what vectors allow us to do is something quite amazing. We wind up, we'll see this very, very soon, and let me take it so it's not quite so 45-degree angle-ish. Suppose I had a vector like this. We wind up taking vectors and getting the horizontal component and the vertical component of the vector. So we kind of break it up into two vectors like this, and then we work with them. And it's amazing how it can take such an incredibly difficult problem and turn it into a very simple problem when you do this kind of thing, break it up. And we'll see that, like, for instance, if there is, now here my artistic ability It's going to really shine through here. So this person has a bullet and he drops it on the ground. And this person is got a rifle. And in that rifle, he's going to shoot this bullet horizontally. And if you take the assumption that the ground is flat, so really our surface of our Earth is slightly spherical, but for short distances it's quite relatively flat. If you take that assumption, if this shoots the bullet exactly horizontally, he drops the bullet at the same time, what happens is the two bullets will strike the ground at exactly the same time. And how do we know this? It turns out that this thing, the theory with vectors, will say this. In the first very small portion of a second, this thing might fall this far. This bullet might go this far and fall this far. Same distance. The vertical distance is being affected by gravity. The horizontal momentum was just given by the gun itself. But we break it up like this, and then, the bullet's slowing down. The next time it doesn't go quite as far. But it's building up downward speed. Goes further in the next portion of a second. And it's going to go down the same, and they're going to wind up striking the ground at the same time. And that's the theory of vectors. And you might say, well, that's just a theory, that's not how it's actually going to work. But then you test this stuff out, and you find out it works just like that. We can break up these forces into these horizontal and vertical components. And then we can make, show things like this, that it's going to be exactly the same time that they hit. Another thing that we can wind up doing with vectors that just turns a difficult problem into a really easy problem is, suppose I have a car great artistic ability. Here's my car, and you've got to push this car. Let's say you ran out of gas. You're on this incline right here, but you're just a little bit away from getting to your driveway. So you get a couple friends, and they're going to help you push this car up a little ways and then off the road. And you might wonder, well, what's the force that you're pushing against? Well, if the car was flat on the ground, I'll just draw this portion with the wheels. The car is flat on the ground. The wheels actually are pushing into the ground, and suppose it's sitting on concrete. The concrete is getting pushed down, and the concrete is pushing back up against the wheels, and this same thing is happening, but it's not going to go anywhere. Here, the same thing is happening over here with the vertical component, or the component this time is not the vertical component, but the component of gravity that's perpendicular to the road. So if you had gravity acting straight down on this, let me get rid of these lines for a minute. Gravity's acting straight down, and it's like, 2,000 pounds of gravitational force. It'll be a portion of this will be perpendicular to the road, and a portion of it will be parallel to the road. And the portion of it that's perpendicular to the road is just like this one right here. It's not causing any movement of this. And it's this portion over here that you're pushing against that's actually, you got to move against that portion to move it up against it. And we could find out what amount of that 2,000 pounds, if we could find out that angle, we could use, just like we did when we solved those triangles in the practice quiz today, we could then find out how many pounds of force that we're pushing against for this bottom portion that's going here. Okay. So vectors will be amazingly useful stuff, and if you take a physics class, you'll be doing vectors all over the place. And so this is kind of our intro to vectors. And two notations for vectors. A, give its horizontal and vertical components. Or B, give its magnitude and the angle it makes with the positive portion of the x-axis. And that's called the direction angle. Let me write it down here. Now, we have a notation that we tend to use for vectors. If we have A, that might be just a number. But if we put this little symbol above it, we mean the vector A. And it's kind of like half of the arrowhead, the upper half, at the end of that. Now, we might use something like this. We put this. This means the magnitude. And you might say, hold it, that's an absolute value symbol. It is. We use the absolute value system symbol, but when it's around a vector, we call it the magnitude of the vector. And we'll see that it has tons of relationship to the normal absolute value. Like it's always positive and it's so on. So it really makes sense to use the same absolute value symbol, but we call it the magnitude of the vector A. And we might say that the angle was like 30 degrees north of west. If we said 30 degrees north of west, what that means is you start by going west, and then you turn 30 degrees towards the north. It would be something like that. And this is the kind of notation for vectors that if you watch the news, that they use. They'll say, the wind is out of the southwest today, and it's 12 mile per hour wind. They're giving the magnitude and the direction. But in math, we prefer this. We would much rather have the horizontal and vertical components of the angle than its magnitude and the direction, because this will be way more useful to us, and we'll be able to do wonders with this. And as remember, both of my examples I was showing you, that it's when you separate them into their horizontal and vertical components, you can get them to act independently and separately and see how they interact and so on. And whew, this unlocks the world to us in math when we switch from the normal format that the usual world uses and we go to the horizontal and vertical component. Horizontal and vertical component, when we do that, the vector looks something like this. We might say the vector A is 1 to the right and 4 up, like this. So there's the vector A. When you put absolute values, things around it, we don't call it absolute value, then we call it the magnitude of that. And we'd give its horizontal and vertical components. Okay. Now, the vector A, that's 1 over 4 up, could be placed anywhere. So it could be if you had an XY axis, you could put, start it over here as long as you went 1 to the right, 4 up. There it is. There's my vector, and I can put that anywhere I want. It's all the same. But when you put it so that its tail, this is the tail of the vector, and this is called the tip of the vector. When you put its tail at the origin, it's called standard position. Standard position of a vector is tail at the origin. And then, so this might be the vector 1, 4. Now, what we need to do is quickly shift from one notation to the other. If we already have it in this notation, we're usually good with it. But very often, the problem that we're given is not in that notation, because it's the weatherman that's telling us the kind of situation. Here, this is the way the wind is going. So it's non-mathematical people will use the second notational format, and oftentimes a problem is stated in that way, and the first thing we have to do is change it to horizontal and vertical components. So if I had let's say a plane, an airplane, is moving at 300 miles per hour. Direction angle degrees, it's like this. This is 300. This is 24 degrees with the positive x-axis. Now, we might say, but I don't want it in this format. I want it in horizontal and vertical components. So, that's a piece of cake for us because we know trig. We go here and here. We're going to make these two vectors from this. And so, let's call this thing x since it's horizontal, and let's call this thing y since it's vertical for a moment. And we can come up with these things. The slow way to do this is to say, alright, what trig function of 24 degrees is going to use x and 300? And so I would say cosine of 24 degrees is SOHCAHTOA, adjacent over hypotenuse. And then I would solve this. Cross multiply x equals 300 cosine 24 degrees. And you could do a similar thing to get the y. But it's faster, more efficient, if you think of it this way. Imagine a tiny unit circle of length 1 coming around here. Then, what would the two coordinates of this point be? It would be the cosine of 24 degrees, comma, the sine of 24 degrees. And then everything has just been magnified out 300 times. So you can just look at that situation and say, the x is the cosine of 24, the y is the sine of 24, but you just stick this magnifying factor of 300 degrees. And there I've converted to the format that I want. Now, I would then maybe punch these out in my calculator. So 300, and then let me check my mode. I want to be in degree mode. 300 cosine 24 is 274.06, and the y is 300 sine 24, 122.02, and then my vector A, in this case, would be written as 274.06, 122.02, given the horizontal and the vertical components. We could, once we had one of these, we could switch back to the other format real easy as well. We would take, if I had been given, so I'm going to erase this. I'll just give it a brief second in case you're taking notes. If I had my vector 1 over 4 up, that's in this preferred format. But if I was, needed to come back to the general public to tell them what I'd found, I might give the wind speed and its direction rather than the horizontal and vertical components of the wind speed. And so, how would I get that? Well, this is pretty easy. This is 1, this is 4. So I use the Pythagorean theorem to get this. And then I got to get this angle. And typically, this angle, theta, you take the tangent of that, and then you get, because it has to do with these two that you're already given. SOHCAHTOA, opposite over adjacent, 4 over 1, so theta will be the inverse tangent of 4. And so we can get those other parts really quick and easy and go back and forth from one notation to the other. Alright, now the big part we need to get to, let me erase this. Is how we add and subtract vectors. And a couple ways when I say it. One is, we call it tip to tail. So, suppose we have a boat in a current on the water, in the river. So here's the wide river, and the boundaries of the river, and the current is going this way. Oh, let's make the current a bit smaller. The boat is trying to go from here to here. The boat would probably do something like this, though. If the boat is, just set off from here and is right about here, it would probably aim somewhere up in this direction, maybe even back a little bit. So that when we put the current with it, how the current's going to go is you just move this current thing. The current was like this. You just move one of those right to here. And then the way you'd actually move would be from that initial point to that end point, right over here. You put these tip to tail like this. We add two vectors together by just putting them, and then go from the very beginning point to the very end tail point, right over here. And when we add two vectors this way, if I was adding two vectors A plus B, and let's suppose that my vectors A are something like this. 5, 1 plus 1, 2. And running out of time here. So on this section we're not getting really far, but it'll be enough to get going with some of the homework. The spot check I'm going to be real light on next time. Just get as far as you can. But let me just draw a quick picture as if the vector 5, 1, 2, 3, 4, 5, 1 is right here. That might be like an airplane. And this might be like the wind. The wind might be 1, 2, but we don't place this 1, 2 necessarily right over here. We could place it tip the tail. One, start at this one where you ended up from here. Go one to the right, go two up. That's the wind. Then this would be my resultant vector from here to here. And what's really cool about that is, let's look at it. The green one, its horizontal components, and the red one, its horizontal components, they just added together to give me the horizontal component of the final one. You just add 5 and 1, and you get 6. And the vertical component of this one was 1. The vertical component of this was 2. What's the vertical component of the whole thing? It's just these two together. Add those two, you get 3. My goodness, these, you add vectors together, amazingly simple if you had them in the right format. Horizontal and vertical component. If you had them with direction, angle, and magnitude, it's totally useless for adding them together. You have no idea how they're going to combine. But when you have them like this, they combine incredibly simply. So just do what you can in the next section, and I'll finish it up on Wednesday. And if we don't get to everything, we'll be fine. We'll just get as far as we get in the next couple times that we have class. And your homework is to get started on 10.8. Do as much as you kind of can reasonably do. And any questions?
Yes. You said
Yes.
You said Wednesday. But you mean Thursday?
Oh, I meant Thursday, sorry. And then Bianca typed in how much should we say in order to say complete, in order to say spot. Let me look real quick. 10.8. How far can you do it? I'm not going to do a spot next time. Just look it over and see what you can do. I'm not sure you're going to get great, but you might want to read a little bit too, and so that it makes a little more sense when I go over it next time. All right, we will stop here. And next time we have class 2, I'll have a practice test for you for the exam 4. And I'll describe what I want you to do with that. I'll see you all on Thursday. You're welcome.